Okay, so the a priori algorithm has shown that we can find all sets K such that the empirical probability of that set in our data is greater than T. Now we want to use this to find association rules. So these rules are of the form the probability of A given B is greater than some other number T, T2, where we split K into two subsets A and B. So the union of A and B is equal to a K, and the intersection of A and B is the null set. And now for every single set K, we want to check all possible splits of that set into sets A and B, such that we can find the conditional probability. And then if that conditional probability is greater than T2, we keep that as an association rule. If it's less than T2, we throw it away. So the question now is, how can we do this efficiently? So first, let's notice that the conditional probability of A given B is equal to the joint probability of A and B, which is the probability of the set K, divided by the probability of the set B. So if the set K is greater than T, and if A and B partition K, then we know that the probability of A and the probability of B are also greater than T. And since the a priori algorithm found all subsets such that the probability of that subset was greater than T, the a priori algorithm also found the set A and the set B separate from their union, and also found the probabilities of those two sets. So the take-home message is that once we have run the a priori algorithm and found all subsets such that their empirical probability is greater than T, we store those subsets and we store those empirical probabilities, and then we can quickly check all conditional probabilities by taking their stored probabilities. So for example, if we're interested in taking K and splitting it into the two subsets A and B, then we know from a priori that we have found the probability of K, so we simply look that probability up and put that in the numerator. From a priori, we also found the set B as being of interest separately from A and separately from K. And so we look up the set B from our a priori algorithm and read off the probability that we found for that one, and then put that in the denominator to get this conditional probability. So we don't need to go back to the data. After the a priori algorithm, we've stored all of the probabilities of the sets of interest. We don't need to then go back into the data to find these conditional probabilities. We can simply take the probabilities that we got from the a priori algorithm and divide the probabilities of interest to get the conditional probabilities. So let's look at an example of what the a priori algorithm learned on a questionnaire problem. So for this problem, we have 6,876 different questionnaires. So that's the number of market baskets that we have. Each questionnaire had 14 different questions, and those are shown here. For example, one question was the person's sex. One question was about the person's marital status. Another question was about the person's age, and education, occupation, and so on. And then those were given different values. So for example, sex had 2 possible answers. Marital status had 5 possible answers. Age had 7 possible answers, and so on. So for example, for marital status, those 5 possible answers were 5 categorical values. For example, single, married, divorced, and so on. For age, they were 7 ordinal values, meaning that age ranges were given, and then you simply said which age range you fell in. So categorical here means that simply that if you were in the first category, there's no ordering of your relationship to the second category. So the categories have no ordering at all. They could be completely reordered. However, the age response has an ordinal relationship. So for example, if you're in the first age bracket, you're younger than the second age bracket, and the second is younger than the third age bracket, and so on. So there's an ordering to these responses. So what we did was created 50, for this problem, we created 50 different items. and we did that based on whether the response was categorical or ordinal. So if it was a categorical response, then however many categories there were that many items. So for example, for marital status, there were 5 different categories, and so we turned that into 5 different items. And so a person has, you can think of a person's questionnaire as being their basket, and for the marital status, they picked one of 5 different items and put it in their basket. So in this case, only one of those 5 items could appear in the basket, and there had to be one of the 5 items in the basket. For the ordinal responses, those were turned into 2 different items based on whether the response was greater than the median or less than the median. So for example, for age, those 7 different responses were binned into 2 different responses. For example, the first 3 values and then the next 4 values. And so we reduced those to do 2 different responses. And so based on this type of an item encoding, it's clear that no basket can actually have every single item. Each basket can only have one of the categorical values for each question and can only have one of the 2 possible ordinal values based on whether it's less than the median or greater than the median. And so this makes it clear that this concept of association analysis is actually more general than simply analyzing customer behavior or purchasing behavior. So now let's imagine that we want to find different rules. We want to find different subsets of high probability. Already with this many items and this many responses, we can't use a brute force search of all the possible subsets, so we have to use the a priori algorithm. So that was what was done. And then let's look at 2 different association rules that were learned from this data set. So for example, based on the questionnaires, there was one association rule that was learned that said, if your language at home was English, and you own your own house, and your occupation is a professional or a managerial category, then there's a good chance your income is greater than $40,000 per year. So let's look at, so for example, for this association rule, this had a prevalence or a support of 13.4%. What that means is that in the 6,876 different questionnaires, 13.4% of those questionnaires had these 4 responses selected. So there were other responses that the people gave in the questionnaires, but 13.4% of the questionnaires of the respondents said that they spoke English, they owned their own home, that their occupation fell in this category, and they earned more than $40,000 per year. So that's the prevalence that we learned from a priori. This subset of 4 objects was one subset that we learned as being of interest. We then took this 4 object subset and broke it into two sets, one A, set A of these 3 objects, and one set B of containing this 1 object, and then learn this rule with a confidence of 88.8%. What this means is that among all of my questionnaires, if the person responded that they spoke English, that they own their own home, and they selected this as their occupation, then 80.8% of the time, they also said that their income was greater than $40,000 per year. 19.2% of the time, they said that their income was less than this. So that gives the confidence. So we can be very confident that if these 3 things are true about a person, then we can be 80.8% confident that this is also true, based only on the questionnaire information. This association rule also had a lift of 2.13. What this means is that I am about 2 times more confident that a person makes more than $40,000 per year if you tell me that these 3 things are true about that person. If I don't get to know anything about the person, then I am only half as confident that that person will make more than this amount of dollars per year. So again, this was only information that we could learn based on the questionnaires. So if the questionnaires are not representative of a population of interest, then all of these rules are bogus. They're not of interest. These rules only apply to the population who answered the questionnaires. And if that population is representative of the population we care about, then these rules will make sense and can be useful to us. If they aren't, for example, if we want to predict what's going on in one state based on questionnaires from people in another state, our rules might be biased in some way, and so we might not be able to trust what we learn from the questionnaires. We also learned a second association rule. So I should say these examples are from the book, The Elements of Statistical Learning. And what the second rule is, simply says that if a person speaks English at home, their income is less than $40,000, they're not married, and they have 0 children, then with 82.8% confidence, their education is less than a college degree. So this is, again, a rule that we learned simply from the questionnaires that we had. This rule had support 26.5%, meaning that 26.5% of the questionnaires satisfied all 5 of these properties. And the lift was about 2 again, meaning that I'm twice as confident that a person does not have at least a college degree if you tell me this information about that person than I would be otherwise. So again, these are all things that we simply can find by counting from the data. We count how many times different things occurred. We calculate these empirical probabilities based on our data. The reason why this is not a trivial task is because we have many responses, we have many data points or observations, and they occur among many different possible objects. So they contain subsets of many different possible objects, meaning that the number of things that we have to check is countably impossible. It would take essentially an infinite amount of time for a computer to check every single possible thing, such that we could confidently say that we found all of them, the things of interest. By running this a priori algorithm, we have a way to very quickly find every single probability of interest, guaranteed, by simply eliminating counting things that we already know in advance will not satisfy our threshold.